So today the topic for discussion is calculus, concepts in calculus, concepts in calculus. Uh, Vinay, are you able to hear me? Please, can you message?
Yes, sir. I can hear you.
Okay, thank you. So, yeah, this is derivatives and its order. Uh, so we have two types of derivatives. One is ordinary derivative and the other is partial derivative. So when we are dealing with a function of one variable, then we talk about ordinary derivative. And when we are dealing with functions of more than one variable, we talk about partial derivatives. All the functions which we are going to discuss are real valued functions. So we, while discussing about the differential equations also, we have talked about this one derivative and its order. So I need not discuss much about that one. But one thing here is that, see, when we are talking about ordinary derivative, when we are talking about ordinary derivative, so if we say like we are dealing with a function f of x, say it is real valued, then the first order derivative, that is df by dx, what we write, we represent this by f. See here in parenthesis I am putting fx. So if we go for the second order derivative, then we represent like this. So in short, if we go to the second order derivative, so we represent that as f in parenthesis x. This is the order. So this is the convention we are about to follow during the presentation. So we represent like this. And when we are talking about partial derivatives, the function involves more than one variable. I mean, so if you take f of x comma y, then in such a case, we represent the associated partial derivatives, for example, with respect to x, as dou f by dou x and dou f by dou y. These conventions we follow. And if you label this one with another variable u, then also we can treat this as dou u by dou x. And this we write as dou u by dou y. So in such a case, we further sometimes, because in this has actually 30 up to 30 slides. I am almost trying to cover all the gate topics here. So ux u subscript y, these conventions it may not be possible to again and again recall. So you stick we may either use either freely, I mean, sometimes we use this notion, sometimes we use this notion, and likewise sometimes we use this notion. When we are dealing with ordinary derivatives also, if you label this f of x as y, then we can say dy by dx. Then see the same idea we can write as represent as dy dx, and in short I write like this. So if we are talking about the second order derivative, if we are talking about the second order derivative, we can write in such a case as d square y by dx square or y2, like this we can. So these are the conventions we are following. Now we'll go to the presentation part. So a different order derivatives we talked about. Then rules for derivative of our function of one variable. You know this one: addition rule, multi-product rule, and quotient rule, and composition rule. This is very important one. That is what I call chain rule. So when we talk about this chain rule, when we talk about this chain rule, of one variable, we are talking about at the beginning chain rule for one variable. So see here, we have something like f of x is, say, uh, sin x, and z of x is, say, e power x. Then we can talk about f circle z of x. What is this? Is called composition. Means f of g of x. This is the meaning. So our f of x is sin x. Therefore, this is equal to sin. In place of x, you have to put zx. Z of x. That is the meaning here. So this is equal to sin e power x. Okay, fine. This we know. This is called sin e power x. So we started from here. F of x is sin x. Z of x is e power x. F circle g is composition here. So sin e power x we have. Now see, if you want, you can treat this. One can treat this as, say, h of x. This f circle g I am writing as h of x. Now see what we are saying: dh by dx we want. No, dh by dx is, it says that df by dz. Treat that as into dz by dx. This is what chain rule says. Okay, so treat g as an object here. So if you have df by dz means f of gx here, we have here f of gx is there here. So f of gx, so sin gx. This f is sin here. So df by dz now. So we will get a cos gx here. So here we will get a cos gx. This is, that is cos gx into dz by dx. If we take our zx is e power x, so you are getting e power x. So this is now equal to, now you can simply put, I write e power x first, followed by cos z of x is again e power x. So the answer is e power x cos e power x. This is called chain rule. So this here you need to notice this one. You need to notice this one. This is called chain rule. So this already we know, but when we are dealing with partial derivatives, in GATE only they focus on partial derivatives. So you first, one should understand this one variable thing. That's why I simply recall this one, right? So now we go to the other one. Yeah. On derivative of function of one variable, we talk about mean value theorems. Most prominent one is Taylor series expansion and Maclaurin series expansion. Here we need not much worry about the Rolle's theorem and Cauchy's theorem. But Taylor's expansion, Taylor's theorem and Maclaurin theorems are important. So see here what the Taylor's theorem says there is that f of x plus h is equal to f of x into the first derivative of x, f at x by factorial 1 into h plus etc. So similarly, Maclaurin series expansion is also given there. See what did this Taylor series expansion says? What this Taylor series expansion says that we need to see. Suppose, see we are here, this is our line. So x tags values on this real line. So this is our x-axis. Say. Somewhere else here, I want to know, I know everything about f. I know about, here this is say small x. I know everything. We know everything about f of x here. We know everything about f of x here. I mean, we know what is f of x. We know what is f first derivative of at x, second derivative of f at x, like that any order derivative we know. That is the meaning of knowing everything about f. Yet x, it is a local one. Now suppose if I want to know somewhere near in this surroundings what is happening to f. So say this point, this point is say x plus h. I want to know what about at x plus h, what is happening to f. So that says that, it says that by Taylor's expansion, f of x plus h, f of x plus h is equal to, I know f of x less than first order derivative of f at x by factorial 1 into h plus second order derivative of x by factorial 2 into h square, like this. So what is happening? See, where is this x plus h? Can we say anything about this x plus h? Yes, this x plus h is h units away from x, that we know. So if you know everything about f at x, then one can know its behavior. What is f at x plus h? That is what the Taylor series says. So here when we consider x as 0, that becomes Maclaurin series expansion. So what is the meaning of that? The meaning here, one can rewrite that. So here, then if you take x as 0, f of h is equal to f of 0 plus f dash of 0, that is you calculate f dash of x and then put in place of x 0. That is the meaning here. Factorial 1 into h plus f second order derivative at 0 by factorial 2 into h square plus etc. But people, in most of the others, they write like this. This is the convention. In place of h, they write x. So f of x is equal to f of 0 plus first order derivative of yet f at 0 by factorial 1 into x plus second order derivative of f at 0 by factorial 2 into x square plus etc. So this is called Maclaurin series expansion. But this plays crucial role in numerical methods and in so see here, For example, if we take f of x as e power x, then what is our any order derivative? You take any order derivative, it is always e power x. What is the meaning of that? F1 of x, if you differentiate once, this is called successive differentiation. F1 of x is e power x, F2 of x is e power x, etc. So, in order to write the expansion here, what is Maclaurin series expansion? For example, what is this at 0, at x is equal to 0? Because because the nth order derivative of f at x is e power x, you can simply write this as e power 0, so it is 1. So once we substitute this in this expansion, so f of x is equal to, then it becomes f of x is e power x is equal to f of 0, e power 0 is 1, plus f dash of 0 by factorial 1. So f dash of 0 is already we have seen it is 1. 1 by factorial 1 into x, plus again f double dash of x is also at x is equal to 0 is 1. So like this you will get, this is called Taylor series expansion, Maclaurin series expansion of e power x. That is what we are getting, e power x is equal to 1 plus x square by factorial 2 plus, like this we are getting. Fine. Right, this is what, like for example, for this one as well as sin x, cos x, log 1 plus x, we knew about their expansions. Standard expansions you can find, you can see that one that I am giving in the material. Now see, right, so this is what about Taylor series and Maclaurin series expansions are functions of one variable here. Now when it comes to the uses of derivative, I'm talking about. See, this is a monotonicity. Monotonicity means, I'll tell you. See here, we are talking about, say, we are labeling our f of x by y. So if I draw the graph, x-axis, y-axis, if the graph appears like this, see here, if the graph appears like this, it is called increasing function. That is monotonically increasing. It is called strictly increasing, I say. And suppose if you have another function, see for example, I will give another function. If a graph is like this, that is, I mean almost parallel to x-axis I am talking about, or something, see, something like this. So for some time same value it is maintaining and then it is increasing. So here this is called monotonically increasing, but because for some time in this place it remains same, it is called monotonically increasing, but it is not strictly increasing, while this one is strictly increasing. Which one is strictly increasing? This is strictly increasing. Similarly, one can talk about decreasing functions also. How a decreasing function looks like, the graph of a decreasing function, it looks like this. So this is called a decreasing function. Monotonically decreasing, strictly decreasing, or just decreasing. Strictly decreasing means, there is an easy way. See, strictly decreasing means just you move this exact line parallel to x-axis. You just like this, if you, it intersects the graph exactly at one point. It is at this point, at this point, at this point. That is called, and because it is moving like this, which way? See, as x is increasing, y is falling. Its value of y is falling. That's why it is called decreasing. So it is monotonically strictly decreasing. That is what we say. But when the function is like this, so when the function is like this, see here, When the function is like this, then it is always constant, neither. So in such a case, this is a constant function. That is what we call, it's a constant function. Now all the cases in terms of first and second order derivatives we can tell. So if f dash x is first order derivative x of x is always greater than 0, then f of x is strictly increasing. If f dash x is greater than or equal to 0, f dash x is greater than or equal to 0, then f of x is increasing, we say. Equality is there, simply increasing, we say. If it is greater than 0, it is strictly increasing, we say. If f dash x is 0, then f of x is constant. If f dash x is less than or equal to 0, decreasing. Strictly less than 0, then it is strictly decreasing. Then f second order derivative of x is less than or equal to 0, then we say f of x is concave, and f2 of x is greater than or equal to 0, it is called convex. See, concave convex means you can think like this. If a function is like this, it is concave. On the other hand, if a function is like this, see here, it is called convex. So if you have second order derivative of x, if you show as, if you observe as less than or equal to 0, then it is always concave. And second order derivative is greater than or equal to 0, it is always convex. I will give some examples of these things. See here, suppose if we take, I'll do one thing. Yeah, right. So our f of x candidate is, say, e power x. What is first order derivative? We'll see. So it is e power x. We know that e power x is always greater than or equal to 0. You cannot say greater than or equal to 0. In fact, you can say that it is strictly greater than 0. E power anything is always greater than 0. So this function is nature, I am telling. It is strictly increasing. It is strictly increasing. On the other hand, if you take e power minus x, then you have first order derivative is e power minus x. This is, see, remember, e power anything is always positive, but you have a negative sign here, so this is less than 0. So this is strictly decreasing. And if we take one more example, see here, say 2x plus 1. If you take that one, then the first order derivative is 2. So it is greater than 0. So it is strictly increasing. I write like this symbol, shortcut. Then if it is minus 3x plus 5, then the first order derivative is minus 3, which is less than 0. So it is strictly decreasing. So if it is either strictly decreasing or strictly increasing, then that function is invertible. Here, what I mean by invertibility, I will tell. See, if you have y is equal to f of x, if it is invertible, then you can express x in terms of y also, and that we write y. So, for example, if it is either increasing or decreasing, see, if f of x is strictly increasing, then invertible. Similarly, if f of x is strictly decreasing, then invertible. In all other cases, you cannot talk about invertibility. Invertibility, I mean, y you can express in terms of x, then x you can express in terms of y explicitly. So, for example, if you take this function, the best choice is or y is equal to e power x. If you have y is equal to e power x, then you can always write x as log y to the base e. So you can always write like that. So invertibility, you can express x in terms of y. And in a similar way, see, for example, we have taken some 2x plus 1 we have taken. We have taken 2x plus 1. So y is equal to, if you say 2x plus 1, then you can easily see that x is equal to half into y minus 1. On the other hand, see, on the other hand, if you take y is equal to x square, you cannot express explicitly in terms of y. But you can say, if you say like this, okay, I agree. You say like this, but two values you are giving. You have to say only one thing. One, then only it becomes a function. That is why this function is not invertible. This function is not invertible. Please remember, from first order derivative also you can tell this same argument. If you, in this case, if in this case we take what is first order derivative of that, it is 2x. But 2x can be, you cannot say that 2x is greater than 0. Because you can only say that sometime when x is positive, it is greater than or equal to 0. And when x is negative, it is less than or equal to 0. You can tell like that. So equality is there. Equal to 0 is possible when x is equal to 0. So neither you can say it is strictly increasing, nor one can say it is strictly decreasing. That's why it is not invertible. Right. So we have talked about this thing, convexity and concavity. For example, the same function you take, if you go for y double dash of x, see here, y double dash x. What is y double dash of x? It is 2 here. So you can say it is always 2, therefore this graph will be like this. You can say it is concave. You can say it is concave. Okay, right? Now, uh, we go to the next slide. Extreme values of function of one variable. Here there is a method, you know, thing how to find extreme values. Extreme value means, I will tell you again using graph. You have, for example, we have a graph like this. Then see, here, at this point you have a peak, say let it be a. At this point you have another low, I mean. So what is happening here? If you draw a tangent at this point, it becomes parallel to x-axis, so its slope is 0. Similarly here, the slope is 0. So if you see this relation as y is equal to f of x, then what we are doing? You simply calculate y dash of x, make it is equal to 0, solve for x, and in such case you will get two. In this above diagram you got two possibilities. Now you look at second order derivative of x at x is equal to a. If it is greater than 0, we say it is maximum. If it is less than 0, we say it is minimum. They are called extreme values. So at this point we have maximum value, and at this point we have minimum value. So that here I explained here. So x0 is called first one, f dash of x naught is equal to 0. It is called stationary point or a critical point. Then f2 second order derivative of x naught is 0, and f2 changes sign from x. I mean at x naught, then x0 is called point of inflection. And see, you have changes sign from positive to negative. Then f of s has local maximum at x0. Similarly, local minimum we have talked about, and uh, that's about local maximum and minimum. I have given the details here. Okay, right. Then the next slide. More on extremums of functions of one variable. You okay, this slide you need not require that, just for information sake I told. Now, okay, it makes complete actually. This is not of much use for you. Now go to the chain rule for functions of two variables, right? When functions of two variables are coming, uh, the thing is that you have, so functions of two variables. So we take like this. We may label this as u or z. U or z. In such a case, we can talk about chain rule. How can we talk about chain rule? That we need to see here. Okay. So here, the possible order derivatives, partial derivatives are like you have ux, uy, they are first order ones, uxx, uxy, same as uyx and uyy. These are the second order derivatives here. Now see how in which way we can talk about chain rule for this one when we are dealing with this type of functions. There are three possibilities here. Though all the three possibilities I clearly mentioned. Suppose u is a function of two variables x and y. U is equal to psi of xy. That is what I told. And z is a function of u. Like see, I'll tell an example here. Chain rule means, so I say z is, because chain rule means composition is coming into picture. So you have, see, z is equal to, what did we say? What is the notation we are following here? Z is equal to, yeah, f of u. So our f of u is, say, e power u, say. And what is our next one here? Uh, u is psi of xy. Okay, good. So we write u is equal to psi of xy according to that notation. So say I write this as say sin x plus y. Good. We'll take that sin x plus y. Then our question is, this is the first case. Can we talk about dz by du? Yes, we can talk about dz by du is e power u. Can I talk about dou z by dou u? It's not relevant because it's a function of u. Z is a function of only one variable. You can talk about dz by du only. On the other hand, if you compose u with z, see, then composing means, if you compose that, what is happening? See, so this can be reviewed as e power, what is u value here? U value is psi of xy, nothing but e power sin x plus y. So you can treat z as a function of only u or z as a function of x and y. But once you treat z as a function of x and y, then in this case you can talk about dou z by dou x. In this case you can talk about zx, zy, etc. Dou z by dou x, dou z by dou y. On the other hand, if you want to treat that as a function of u only, then you can only talk about dz by du. Now my question is, how can we see, if you can directly compute from here what is by dou z by, what is dou z by dou x? We know that it is dou z by dou x is nothing but zx is, I mean dou z by dou x is nothing but e power sin x plus y. But what is the derivative of sin x plus y with respect to x? Cos x plus y. This is how we'll get the answer. But what is this? See here, the important thing is this. and this object. This is nothing but dz by du. What is dz by du? See, look here. Dz by du, if you take e power u only, e power u only, that is e power u. But what is u? See here again, u is psi of x, that is sin x plus y. So you are getting this as e power sin x plus y. Okay. And now what is I mean the other one, this one, that is you are simply taking dou u by dou x, that is cos x plus y. Dou u by dou x is cos x plus y. Of course, dou u by dou y is also cos x plus y. So here the chain rule is coming. How the chain rule is coming, you can see here. See how the chain rule is coming. You can see here, dou z by dou x is equal to dz by du into dou u by dou x. Similarly, dou z by dou y is equal to dz by du into dou z by dou u by dou y. So this is one possibility. The other possibility is this one. See, u is, see, first this is only one variable function and we are composing with this. Now you are taking this, and x is a function of one variable, y is a function of one variable. In such a case, the chain rule appears as you can only talk about du by dt only, because see, this can easily be felt. This can easily be felt. I'll show you. So for example, our f of xy in this context is, say, uh, x square plus y, simple term, or x square plus e power y. Now say x is equal to 2t, y is equal to sin t. If you have like this, then I can talk about, if you label this as u, I can talk about what is du by dt. You see, one way is you are treating u as a function of x and y. Another way is you can treat u as a function of t only. How can we treat u as a function of t? You can treat u as a function of t as, because with this one in mind, so x square is 2t whole square, 4t square plus e power, e power y, so e power sin t. You are getting this. So if I ask you what is du by dt, you will get 8t plus e power sin t is e power sin t, and for sin t the derivative is cos. And you can get the same answer in a different way. That is, that way is here. That way is here. That way is here. And the third case is you have z is equal to f of xy, and x is also now a function of two variables u and v. Y is a function of two variables. Then you can talk about dou z by dou u, dou z by dou v there, dou z by dou v, and you have this. So when we are talking about chain rule involving functions of two variables, these three cases will come. These three cases will come. Right. When we look at the problems, you can easily see, and so quickly we'll move to the problem session. Okay. Right. Then this is what we call implicit function. You can see if it is necessary, you can look into this one. There is simply a relationship here. Okay, I will also, this also I'll explain. You have x square plus y square is equal to 4. This is something like f of xy, the left hand side, this one, is equal to constant. This is c. Now, if you want to know what is dy by dx, he says you write, see there. What did they say? Here there is a formula, dou f by dou x by dou f by dou y. So you have, he says, fx by fy. So fx you can write there, fx is 2x by, you have 2y, so x by y will come. So that is here what we have. Then go to here. Euler's theorem for homogeneous functions. This is very important one. Most of the questions come from this combined with this rule. This rule. I'm sorry. This rule. Chain rule involving functions of two variables. You need not worry about the implicit functions, but Euler's theorem for homogeneous functions. That some questions, most of the questions come from this one. So if your function f of xy is like this, f of tx ty is equal to t power n into f of xy, then it's called a homogeneous function of degree n. In such a case, x dou u dou x plus y dou u dou y is n into u. And similarly, if you have dealing with the three variable functions, you have f of x y tx ty tz is equal to t power n into f of xyz. Then it is a homogeneous function of three variable of degree 3, degree n. So in such a case, you have this Leibniz version with three variables function. Okay, that we will see applicate. Now, Taylor series and Maclaurin series expansions for functions of two variables. See, when I am, this is same extension we are doing. You have two variables now, x plus h, y plus k. So you have f of xy. Now what is factorial? One, you have to look at, yeah, one has to see what is this. Okay, I will explain this. Where we need to understand is this part. What is the meaning of this? So if I ask what is h dou y dou x plus k into dou by dou y applied on f of xy means simply h into dou f by dou x plus k into dou f by dou y. That is the meaning. Okay. Similarly, in short, I am writing like that. But see, look here. Easy to remember that. That's why I gave this representation. Right. Okay. Okay. Now see, you look at this square part. Starting from here, here applied on fxy. What is the meaning of that? So h dou by dou x plus k dou by dou y whole square applied on f of xy means you simply a plus b whole square like that you do h square into dou square by dou x square. Square means this k square dou square by dou y square plus 2hk into dou square by dou x dou y. That's all. You put simply f, f, f. That's all. That is the meaning. So I have given Taylor series expansion as well as Maclaurin series expansion for functions of two variables. Sometimes they will give this. That is why. Okay. Okay. Right. So this is mentioned here. So next slide is extreme. This is another slide that is important. 13 slide is uh, from for most of the gate questions will come from, you have to use this slide and this 11 slide and 9 slide. Slide number 9, 11 and 13. They are important ones. So this is about two variables, two variables, how to find, talk about extreme values. So dou f by dou x, you make it easy. See, first given f of xy as real valued, then at xy is equal to ab, first order derivatives becomes 0, then ab is called a stationary point. Now what we are doing, once stationary point is determined, then what is the value of r? What r represents here? You, you simply calculate r, s and t represent respectively the second order derivatives of f with respect to x, with respect to x and y, with respect to y. So we compute those things. If rt minus s square is greater than 0 and r is less than 0, then f of xy has a maximum at ab. If it is rt minus s square is greater than 0 and r is greater than 0, then f of xy has minimum at ab. And similarly, for rt minus s square is less than 0, you need not worry about the signs of r. So f of xy has saddle point at x ab. And if rt minus s square is equal to 0, we cannot draw conclusion based on second order derivatives. Okay, so this is one important slide using which we do some problems. This is 13, right? Now come over to 14, the idea of Jacobian here. So Jacobian means you have two relations. I mean, u in terms of x and y is there, and v in terms of x and y. Then j means dou u dou x, dou u dou y, dou v dou x, dou v dou y, that we are taking, and that is what we call Jacobian here. Usually it comes for transformations. I will tell what is transformation. In case of three variables, you have the Jacobian is like this. So you please remember here one thing. Easy to remember Jacobian. Use of Jacobian will directly go there. See here, you look carefully. U is there along row. Same here. V. Now columns, x column, y column. So you have u, v, x, y. Similarly, here you have u row, v row, w row, x column, y column, z column. Like this, you see, it is determinant. Jacobian is nothing but determinant. Okay. Right. Then go to some properties and applications of Jacobian. I will tell this one. This is also important slide. So this is slide number 15. So see here, when you have, this is what we call composition functions, Jacobian, how Jacobian appears. So u is a function of r and s, and v is a function of r and s, and r is a function of x and y, and s is a function of x and y. Then you can talk about, this is called chain rule, first one. The second one is, if you have u as u and v are expressed in terms of x and y, and the Jacobian is 0, then not equal to 0, then x and y also can be expressed in terms of u and v. That is the second point which says, and its Jacobian is 1 by j. And the third point, when you come to that one, if Jacobian is not equal to 0, then u and v are functionally independent, we say. If the Jacobian is 0, then they are functionally dependent. So this slide 15 is also important. 15 along with the definition 14 is important. Okay. So slide number 13 is important. Slide number 15 is important. Problems will come on that. on those things. Now when we go to implicit function, you need not worry about that. Now okay, now then we will go to integral. So I covered here during this 1 hour session quickly the idea of differential calculus of real valued functions of one variable and real valued functions of more than one variable. When you are dealing with the differential calculus of real valued function of only one variable, then the ordinary derivatives will come into picture. When we are dealing with the differential calculus of real valued functions of more than one variable, usually it is two variables in gate or three variables, then partial derivatives will come into picture. You need to look in three angles here. The first one is chain rule, the second one is Leibniz rule for Euler's rule for homogeneous functions, third one is that is what we call functional dependency and independency. On these three most of the questions will, and fourth one is extreme values. On these four only maximum questions will come. So we will now start solving some gate questions. We'll try to solve. So we will try to solve now some gate questions. Right. See, take up another one. Right. So these are the questions. We'll try to solve. Okay. See, first, if u is equal to sine inverse of x square plus y square by x plus y, then dou u by dou x plus, here there is again a mistake, printing error, y dou u by dou y is there, is. So what is given here? Some printing errors are there here. U is. So it is given that u is equal to sine inverse x square plus y square by x plus y. And what we need to calculate? X u subscript x, that is dou u dou x, plus y u subscript y, that is dou u dou y. What is this he is asking for? See, in order to answer this one, whenever you see this, please, a hint is that try to apply Euler's theorem for homogeneous functions. Where is that? Right, this is the one. So we need to think about homogeneity. Here, one can see there is some difficulty here. You need not calculate any partial derivatives here. See, first I need to check whether this u is a homogeneous function. Observe one thing. If you look at this part, okay, say that is I call this part z. So z is a function of x and y. Okay, you can call it z. Then okay, we need not even call it z. In a simple way we can do. Okay, now see, you call it z. Okay, if you call it z, my question is, z is homogeneous. Z is homogeneous function of degree is also important here, 2, of degree 1 it is 1. How? That we'll see. How we'll see. So you are, what is your z here? Z is a function of xy, I told. Z of xy is x square plus y square by x plus y. To check homogeneity, you need to see what is ztx comma ty. So it is t square into x square plus y square by x plus y. Sorry, by t into x plus y. In place of x, you are putting tx. In place of y, you are putting ty. So this is equal to t into x square plus y square by x plus y. So this is nothing but t into z. So we got that z at tx ty is nothing but t into t power 1 into z of xy. So this is a homogeneous function of degree 1. This is a homogeneous function of degree 1. So here we treat the degree by n. N is 1. On the other hand, this if you take u is not a homogeneous function of x and y. Why? See, if you u of x xy, if you take, what is that? Sine inverse x square plus y square by x plus y. What is u of tx comma ty? U of tx comma ty is sine inverse of tx whole square plus ty whole square by tx plus ty. Nothing but is equal to sine inverse t into x square plus y square by x plus y. But this is not equal to t power something into, what is that thing? Okay, t power something into u of xy. That is the problem here. You cannot pull out that t. So u is not homogeneous. That's what I'm saying. U is not homogeneous. Z is homogeneous. So what we will do is that because Z is homogeneous, I can write this thing as, okay, Z is equal to sine u. Z is equal to sine u. If you write this as Z is equal to sine u, clearly sorry, clearly Z is a homogeneous function of u and clearly Z is a homogeneous function of x and y. We know that thing. So right. Right. So what can we say? Z is a homogeneous function of x and y of degree 1. So we can say that, right, dou z by dou x plus dou z by dou y is equal to nz. We can say by Euler's function, by Euler's theorem. That is x zx plus y zy is z. That we can say. But see, what is zx? Here I am applying that chain rule. Okay, zx is dou z by dou x, that is. Okay, dz by du into dou z by into dou u by dou x plus dz by du into, okay, sorry, that is enough. Right. So what is dz by du here? What is dz d dou z by dou x is equal to dz by du into dou z by dou x. Nothing wrong in that, right? So in such a case, yes, what did they ask for? Yeah, dou u by dou x. Dou u by dou x they asked for. Okay. Dz by du is equal to, we want ux, no? Right, right, sorry. Ux we want ux, sorry. So here dou u by dou x, nothing but du by dz into dou z by dou x. What is du by dz? Here you have to get du by dz. Somewhere I'm going wrong. Du by, no, small mistake. Just it will come very easily. Just a minute. Just a minute. Because the answer will be here. Uh, the answer will be tan u. It will come as tan u. Because degree is 1 here. It comes as tan u. So how quickly tan u we will get? Just a minute. This x into dou u by dou x. Tan u I have to get. So I need to write dou u dou x. Just a minute. Yeah, right. Dou u by dou x I'm writing here. Dou u by dou x, how can we write? U is a function of which one we have to take? Dou u by dou x. Tan u will come here. Just a minute. Tan u. Somewhere else I missed it here. Dou u by dou x. Dou u by dou x is here. Look at that slide. Better looking at that slide. Dou u by dou x. Okay, just a minute. Here, yeah, this slide is. So we have, right, agreed. So it is z is a, we are in this case, right? We are in this first case. So, right, dou z by dou z by dou x, good. So we want du by dx again, right? I'm in right direction, right? So dou u by dou z plus d into d dou z by dou x. Okay, good. What did I write here? Dou z by dou x. Where is dou z by dou x? I stuck here. This we know. Yeah, right. This we have to use. So it is simply right. It is equal to du by dz good into zx, right? Into zx. Similarly, small thing. Similarly, dou u by dou y is equal to du by dz into dou z by dou y. Okay, done. That is equal to du by uh, right, du by dz into zy. Okay, right. Now what we are asked for? X. We are asked for Here it is. Yeah. X dou u dou x plus y dou u dou. X dou u dou x plus y dou u. Right. So therefore x dou u dou x plus y dou u dou y, right, is equal to x into, right, dou u dou x is du dz into zx. So what I into zx plus y into zy into, common thing is there here, du by dz is common. Du by dz is common. Oh, right. But what is x dou u dou x plus x dz x dou z dou x plus y dou z dou y? It is already here mentioned. See, this is here already. It is mentioned. That is z. So is equal to z into du dz. Z into du. What is du dz? Okay. What is du dz? We started from here, right? What is du dz? Du dz is, what is du dz? Du dz. Here du dz. Here only root. Yeah. Du dz is, see here. If you apply both sides here, the z thing. So dz is cos u du. Cos u du. So du dz is 1 by cos u. Du dz is 1 by cos u. Somewhere here du dz is, so z by cos u will come. Z by cos u will come. Somewhere here I missed it actually. Sin u also has to come. Okay, we will see. Please check this one. You will get a tan u. Somewhere I have missed this. Somewhere we observed that. We need not waste much time. Right. Z is a function of homogeneous function of degree 1. So we got x into dou z by dou x plus y into dou z by dou y is z. Yes, we got that. Then du dx we have taken. Now x du dx plus y du dy we have to calculate. So du dx is here. Du dz we have taken common. So this is equal to z into du dz. So it is coming as, here's one sin u will come. Where is that I'm missing? Oh, yes, right. Sorry. Z is sin u. That we need to put. That I forgot. Z is sin u. Yeah, right. That is equal to sin u by cos u. Yeah, right. It is 10. I'm sorry. Took more time. So, sorry. So tan u is coming. Right. It is 10. So what I mean to say is that this slide, if you practice, if you practice, here the crucial step is, one need to remember is that you have to make use of these things which we took from this slide, this one, the first case. Okay, now we look at the other example. The second example is also similar to that one. The second example is also similar to that one, you can see. And the third one, x is r cos theta, y is r sin theta. Then, so, right, x is r cos theta, y is r sin theta. X is r cos theta, y is r sin theta. Once this is known, see x square plus y square is equal to r square. This is also you can easily see. Okay. Now what he is asking for, we need to check what is dou r dou x. Okay. What is dou r dou x and what is dou x dou r and dou r dou x. Okay, we'll see that. Dou x dou r. Okay, right. We'll calculate dou r dou x and dou x dou r. Okay, good. So what is dou x dou r? Dou r dou x is nothing but you can get from this one, right? Good. So both sides of this you apply, both sides to of this equation you apply dou. Good. That's an idea. So from here, dou by dou x I am calculating x square plus y square is equal to dou by dou x of r square. Okay, that implies left hand side is 2x. Here right hand side is 2r into dou r by dou x. So from here we can see that dou r by dou x is x by r. Dou r by dou x is x by r. Now what is he asking? Dou r by dou x is not equal, 0 is wrong. Dou x by dou r is equal to 0 is also wrong. Dou x by dou r is equal to 2, he says. Dou x by dou r is 2, he says. That option we have to see. Dou x by dou r. Dou x by dou r, it is cos theta. Dou x by dou r is cos theta. So that is also wrong. Dou x by dou r is cos theta it is. Now dou x by dou r and dou r, again so many mistakes in this one. 3. Let me see the answer. For third question B he says. Okay, for third question B he says. So if it is 3, dou x by dou r is dou r by dou x. Dou r by dou x. Dou r by dou x is how can I get? Okay, good. Now from that, right. X is equal to r cos theta. X is equal to r cos theta. You apply both sides. Dou x by dou x you can write. Okay. Dou by dou x of, what is the second one here? We have just calculated dou x by dou r we need to calculate. Dou x by dou r we need to calculate. Dou x by dou r is equal to cos theta only. How can cos theta is equal to x by r? Yes. X by r, x is r cos theta. So r it is cos theta. So B is correct answer. So B is correct answer, right? Fourth one, z is f of xy. X is equal to e power 2u plus e power minus 2v. Similarly, y is a relationship between u and v. Then we need to find what is dou u by dou f by dou u plus dou f by dou v. Okay. So in this case, we got dou x by dou r as dou r by dou x. This is okay. B is the answer. Now the next question. Now the next question. X is okay. X is equal to e power to u e power to x is equal to e power 2u x is equal to e power 2u plus e power minus 2v plus e power minus 2u and y is equal to e power minus 2u plus e power 2v e power 2v, right? And z is a function of x and y, and z is a function of x and y. Okay, this is given. Now what we need to find? Dou f dou u minus dou f dou v. Dou f dou u minus dou f dou v. So dou f dou u minus dou f dou v. What is this? We need to find. Okay. So we calculate, and the choices, we'll look at the choices is expressing in terms of dou f dou x dou f dou y. So dou f dou u will calculate dou f dou u. So dou f dou u is equal to okay, right, dou f dou u is equal to, right, dou f dou u is equal to dou z dou u, that is equal to okay, that is equal to yeah x dou z dou x into dou x dou u plus dou z dou y into dou y dou u, right, dou y dou u. So this is equal to this is equal to this is equal to uh, dou z by dou x. I keep like that. Dou x by dou u, you can easily see here. Dou x by dou u is 2e power 2u, is 2e power 2u. So 2e power 2u into dou z by dou x plus okay plus plus the other one dou y by dou u. Dou y by dou u, if you look at dou y by dou u minus 2e power minus 2u minus 2e power minus 2u into dou z by dou y. But z is nothing but f, so it is equal to so it is equal to okay, we write here is equal to 2e power 2u f x minus 2e power minus 2u fy. Okay, right. What is this? Dou f by dou u. This is dou f by dou u. Similarly, if we want dou f by dou v, if we want dou f by dou v, dou f by dou v, is nothing but is nothing but dou f by dou x into dou x by dou u dou f by dou x into dou x by dou v plus dou f by dou y into dou y by dou v. So here dou x by dou x by dou v is v minus 2 e power minus 2v minus 2 e power minus 2v minus 2v into fx. Next dou f by dou, here there is right me dou y by dou v dou y by dou v dou y by dou v, we have to see here dou y by dou v, it is 2 e power 2v, it is 2 e power 2v. So plus 2 e power 2v fy, right? So the now the conclusion is we have dou f dou u. So fu I write fu is here we have written uh, 2 e power 2u fx 2 e power 2u fx f subscript x, okay, uh, fx right, minus 2 e power minus 2u minus 2 e power minus 2 e power minus 2u fy fy. Similarly fv is equal to minus 2 e power minus 2v fx plus 2 e power 2v fy. Now fu minus fv he is asking for fu minus fv. So fu minus fv is equal to, so fx I can common take common there. So 2 will come here, e power 2u plus e power minus 2v fx. Now minus will come common here, 2 e power minus 2u plus e power 2v minus plus just right, plus will come, this minus this, so v f v fy, right? Now e power 2u plus e power minus 2v e power 2u plus e power minus 2v is nothing but x. So this is equal to 2x fx, okay, e power minus 2u plus e power 2v e power minus 2u plus e power minus 2u plus 2v is nothing but y. So this is minus 2y fy. So it is 2 into x fx minus y fy. This is will be the answer. Yes. So the answer is What did he say again? Fourth question. Fourth question is A. He says. Fourth question is A. So do you do f do u minus do f do v. Do f do u minus do, yeah, there is y is not there, is not printed here. So y is not printed here. So our answer, see here, y should be there. No, something. What is some? Y should be here. Where is this? I'm not able to see. Something software. Okay. So here y is not there. A is the answer. We got already that answer here. So yeah, right. We got this right. So why it is not. Right. Fourth question is right. So for this one, what I mean to say is that this third is first. We have seen first one and the third one. Chain rule for two variables. This third one, right side part, we have used. We have used the right hand side part. So fourth question, that is. Fifth question is also similar one. He is asking for f. Okay. Do right. Right. We'll see that. Z is f of xy. Z is f of xy. X is r cos theta. Y is r sin theta. Right. So from this one, we need to find what? Dou f by dou x whole square plus dou f by dou y whole square. Okay. So we need to calculate dou f by dou x here. So dou f by dou x. Right. Okay. So third part only, it dou f by dou x we want. Dou f by dou x is nothing but dou f by, because we are looking for answer in terms of r and theta, dou f by dou r into dou r by dou x plus dou f by dou theta into dou theta by dou x. So that is the first one. Similarly, dou f by dou y, that also we require. Dou f by dou r into dou r by dou y plus dou f by dou theta into dou r by, sorry, dou theta by dou y. That we need to solve. So what we require? Dou r by dou x, dou r by dou y, dou theta by dou x, dou theta by dou y. How can we get that? See here, dou r by dou x, dou r by dou y, right? Dou r by dou x. So now see, x is equal to r cos theta implies dou r by dou x if you want. So both sides you apply dou by dou x. Dou by dou x of r cos theta. No, this is not required actually. Yeah, we can get one stroke all the answers, right? Y is equal to r sin theta. right? This implies x square plus y square is equal to r square. So we have dou r by dou x, dou r by dou y we want. So now here we apply both sides with respect to x. So you have 2x is equal to 2r dou r by dou x. Then 2y is equal to 2r dou r by dou y. See, we can substitute this dou r by dou x, dou r by dou y here. So this implies dou r by dou x is equal to x by r, comma dou r by dou y is equal to y by r. This is okay. Now we need to look at the other one, that is theta also. In terms of theta also we have to do. So how can we get tan theta is equal to y by x, another relationship. Tan theta is equal to y by x. Why we require this one? See, already we got dou r by dou x, dou r by dou y. Here we need to require dou theta by dou x, dou theta by dou y, right? So dou theta by dou x, both sides we apply with respect to x differentiation. So dou tan theta by dou x. So dou tan theta by dou x is tan theta is secant square theta derivative secant square theta dou theta by dou x is equal to this side, right side, y by x with respect to x we are doing by keeping y as constant. So minus 1 by x square. So minus y by x square will come here. And similarly with respect to y if you do, secant square theta dou theta by dou y is equal to 1 by x. That will come. So, right. Now what is y by x? Here already we have seen. What is y by x? Here I will write y by x is tan theta. Y by x is tan theta. So y by x is tan theta means, so right, y by x is tan theta, right. We need to substitute these values here. Already dou r by dou x is there, dou r by dou y is there, dou r by dou x is there, right, dou r by dou y is there. And we are looking for the answer. Okay, good. Dou r by dou x is there, dou r by dou y is there, dou theta by dou x and dou theta by dou y we want. Dou theta by dou x. Dou theta by dou x is secant square theta what is secant theta? Secant theta is, right, okay, 1 by cos, right. So good. So this implies dou theta by dou x is minus y by x square cos square theta. Cos square theta. So this is x is r cos square. So minus y by r square this is. minus y by r square. This is minus y by r square. This. Okay, good. And what is dou theta by dou y? Dou theta by dou y is dou theta by dou y is 1 by x into secant cos square theta. X is again 1 by x. 1 by x into cos square theta. So this is x is again r cos theta. So we have cos theta by r cos theta. R will come. Cos theta by r will come. Okay. So this is nothing but we need to convert the whole thing into uh, x, y, and r. So cos theta, right? But what is cos theta? Cos theta is here. Cos theta is x by r. Cos theta is x by r. So this is equal to x by r square. Is equal to x by r square. Right. So we have finally on dou theta by dou x. In short, we write as theta x as theta x as minus y by r square minus y by r square, and theta y is x by r square, and Rx is x by r, Ry is y by r. Rx is x by r, Ry is y by r. Okay. So now we need to go here. Fx is Rx dou f dou r. Fx is Rx Fr, I write, plus right, theta x f theta, theta x f theta, and similarly fy is ry fr plus theta y f theta, right? So the first one, this is the first one. So this one, I mean, this one, okay, that one we need to write. Fx becomes, right, Rx Fr. So Rx is x by r, right? X by r Fr, theta x minus y by r square f theta, minus y by r square f theta. On the other hand, this is this is okay, ry Fr, ry is y by r, So we have y by r fr, y by r fr, y by r fr, theta y. Theta y is x by r square, x by r square f theta, x by r square f theta, plus, sorry, x by r square f theta, plus x by r square f theta, f theta, right? Okay. So now we want, what did he ask for? He asked for fx whole square plus fy whole square, fx whole square plus fy whole square, fx whole square plus fy whole square. So fx square whole square means fx square is nothing but, just here we calculated, x by r fr minus x by r fr minus x by r fr minus y by r square f theta, y by r square f theta whole square, right, and fy square, and fy square, and fy square is, fy square is, fy square is y by r fr, y by r fr, y by r fr plus x by r square f theta, plus x by r square f theta, plus x by r square f theta whole square. So here x by we need to take x by r is, what is x by r cos theta, that is you can take cos theta. Okay, this further we can write, this as, you can take r square common here, so xr fr minus yf theta whole square, okay, by r power 4, this is by r power 4, and this is equal to yr fr plus xf theta whole square by r power 4. So now uh, we need to calculate plus sum of these two squares, sum of these two squares. So if you take sum of these two squares, okay, what we will get? You have xr fr whole square. So sum of these two squares, xr whole square fr square plus yr whole square fr square, okay, plus this is one term, the another square term here is uh, y of theta whole square. So y of theta whole square, y of theta whole square. So here y square f theta square, in this next one x square f theta square. So plus x square f theta square, okay, right? That is okay, these two. Next 2ab terms are there. 2ab means 2xy, 2xyr, 2xyr. minus 2xy r here. So plus minus 2xy r in the other one. What is there? Uh, plus 2xy plus 2xy r plus 2xy r plus 2xy r into fr f theta. Fr f theta. So these two things will get 0. Now you have x square plus y square is r square. The whole by r power 4 is there. Okay. So here x square plus y square is r square here, and here if you look at, this is x square plus y square is r square. Okay, r power 4. So what we are getting here totally what we will get is r square r power 4. Good. R power 4, this is equal to r power 4 r square we can take, right? R power 4 fr square plus r power 4 fr square plus, here you have r square, here we have r square f theta square by r power 4 you will get. So this is fr square plus 1 by r square f theta square. We need to check this computation to be careful because while scrolling. So yeah, right, C is the answer. Yes, C is the answer. So I think for this fifth question, C is the answer. Fifth question, C is the answer. B you are hitting. No, we have to get C. We have done this one correctly. It is C. Fifth one. 4 is. This is sixth. Where is fifth? Oh, sorry. Fifth one. We have to get C as the answer. We got already C as the answer here. Okay. So for today, I will close, and the remaining problem we'll do in the next session. The remaining problems we will do in the next session.
Thank you, sir.
Okay.